People have bad gastrointestinal toxicity, throw up, and you know, these are tissues that kind of are replaced faster than some of your other tissues. And so you get this toxicity because the poison is not targeted. It goes everywhere. And in the old days, you know, this is a kind of a famous phrase. It's let's kill the tumor before we kill the patient. It's amazing. You know, I'm involved in clinical trials, and you know, it's very saddening if someone on the trial dies due to our therapy. And we fortunately haven't seen that. But there are lots of therapies that are being tested right now that do cause death because it's too toxic. So the better way is targeting the drug, and in using the same illustration, you inject that red drug, and instead of going everywhere, it just finds the tumor. That's what we want. That's the goal. How do you accomplish that goal? So before any of you were born, I'm talking about the students, probably most everybody else in the room, published a paper with Phil Lau, who is my mentor from Purdue. I went to graduate school in Purdue. And I came up with this way in his laboratory of delivering molecules into cells by, and I think you'll be able to relate to this. It's sneaking the drug into the cell. The cell doesn't know it's going to get it. And I'll explain how that works in just a second. But what I did is I took something that every one of you gets every single day. That's a vitamin. It's called folic acid. If you look on your cereal box, it'll be one of the many things that's added to your cereal to fortify it. It's also added these days to breads and pastas and so forth. But what I found out is that this form, you know, obviously introducing chemistry, many of you probably have had chemistry already. This is what folic acid looks like at the chemical level. And what I knew is that this portion of the molecule, all the way over here, that was responsible for binding to a cell surface receptor called the folate receptor. However, this part was not. And so what I invented is a way of attaching drugs to that site such that I didn't disturb folate's ability to bind to its receptor. Turns out that folate's receptor is highly specific for cancer. There's another way that this vitamin gets into cells, but conjugating, and that's a fancy word of attachment, conjugating something to that site made that vitamin impossible to get into normal cells, unless it had the folate receptor, which the expression of this receptor was really unique. It was more geared towards being on cancer. And so if you consider this as the surface of a cell, a cancer cell, and this is the receptor, we want to target. We want to sneak that drug into the cell. The cell thinks it's getting a vitamin to help it. And folate happens to be a very important vitamin for the cell to be able to make DNA. And think about it. If it's a cancerous cell, that cell wants to divide, keep dividing. But before it divides, it has to double its amount of DNA, right? If it doesn't have folate, it can't do it. I'm advancing myself here, sorry. So here is a derivative of folic acid, and I put in blue the extension off that one site. These are just 3 amino acids. We don't need to go into the detail, but those 3 amino acids were selected specifically because they can wrap around, or the fancy word is called chelate, and chelate technetium. Technetium is a short-lived radioactive atom. It's used for nuclear imaging. You ever go to a hospital and see nuclear medicine and all that? This is part of that. This is imaging. And we created this compound. It's called EC20, or etarfolitide. I may use both interchangeably. And the idea is if a cancer cell has the receptors on the cell surface, we want to park EC20 on that receptor. And it binds, just like a key goes into a lock. It's very specific molecular interaction. So having done that, we can give mice tumors. We typically put them on their back flank area. These are human tumors, and we have special mice that allows those human tumors to grow on those mice. And it will eventually kill the mice if they're not treated or cured by some other means. But we test this where we give the mice tumors, and then we inject the radioactive form of EC20. And after a period of time, typically a few hours, we will euthanize the animal and measure in their organs how much that compound made it in. And if you look, so this is the percent injected dose per gram of tissue. This is all background levels of radiation, but look at the kidney and look at the tumor. It went to both. Why? Because the tumor has folate receptors. We knew that before we inoculated the animal. But naturally, the kidney does too. When we image this mouse, we can see, we put these 2 human tumors on their back and they glow. So do the kidneys right here. Why do the kidneys have folate receptors? Well, it's a consequence of natural biology, but the folate receptors there are meant to reabsorb folates and get them back into your bloodstream. That's really the function. But also the kidney is a route of excretion. This was not a big surprise to us, but when you're thinking in terms of targeting the receptor for therapy, targeting cancer, that could be an issue because we could potentially harm the kidney. We'll come back to that in a little bit. So going back to this image here, right here, where we have the radioactive technetium, we can image patients. And so we will get what's called a SPECT image, single photon emitted computer tomography. And here we have a woman who had metastatic breast cancer and had a lesion on her skull. And anywhere where it's dark is where that radiation has been parked. Right? So we said, they knew that she had a lesion here. What information this told us when we injected this EC20 compound is that lesion, those cancer cells there, have a folate receptor, because if they didn't, we wouldn't see any dark spot there. Likewise, this guy who had a pituitary adenoma right smack in the middle of his brain, we lit that up. Okay, here we go. We can also do fancy work with computerized tomography, very sensitive thing. Here is an ovarian cancer. Now, I put this up here to show you that if you look in the plane, this axial plane as they're imaging the entire body, this is what you'll see. So this is the internal organs. It's just a slice through the body. But if you look here, if you're not a trained pathologist, you may not know there's cancer. Or if you are trained, you say, this doesn't look normal. There's something going on here in the liver. And actually, this is ovarian cancer, which starts in the abdominal cavity, but then it just spreads everywhere. It coats all the organs. And we took a SPECT image looking where the radiation is, the short-lived radioactivity, and look, it coincided with that area that was abnormal. In fact, we could fuse those 2 images and put some fancy color around it to really make it obvious where the cancer is. This helps the clinician. It says, this is where it is. It may help them to even cut out the tumor if they can, if that's an option. So we have used our, this is awfully slow, I apologize. There we go. We've used this knowledge of imaging to develop drugs to target, to kill the cell, to kill the tumor. And what we came up with was something called an SMDC, which stands for Small Molecule Drug Conjugate. It has 4 different modules. The first is, think of this as folic acid, but it could be something else too to target different tissue. Because why? Well, the cell wants this. The cell wants this. It doesn't care about this. In fact, it doesn't want that because that's going to kill it. So we attach that potent drug, or in some cases we'll call it a warhead. And we use fancy words too. So we attach this drug to the targeting ligand. The chemistry of how we attach those two is very important. Not important for today's discussion, but it is important on how you connect them. So those of you that are interested in chemistry, contact me. I can talk to you more about this. But what happens, and if I can have you press the button, this is a video of what we know goes on. So here we have the SMDC. It's approaching this tumor cell that has a folate receptor. And it's going to bind just like a key going into a lock. It's going to trigger this membrane to pinch inward. And that process is called endocytosis. That's the company, we derived our company name from that, endocyte, as you can see. So these vesicles come in here, and through those chemistries that I didn't really go into detail, what happens is once it's inside the cell, the conjugate breaks apart. And the drug, in this example, is going to go in the nucleus and kill it, or stop DNA synthesis and so forth. And the green tumor cells get killed, whereas the blue normal tissue is fine. So that's the idea, specifically targeting a drug, masking that drug so it doesn't go into normal cells and hurt the normal cells, but only go to the cancer cell where it can unload the payload and kill. So does this look familiar? At least I know the ninth graders saw this again this week. The cell cycle. Who cares? Who cares about the cell cycle? Well, I'm going to give you a reason why. So again, you're in school, you learn about the different phases. Someone talks about a G2M transition. Well, unless you're embedded in the molecular biology and the use of that knowledge to help treat a disease, it probably won't matter. But watch this. We know that during the mitotic phase, which is broken apart into different subphases, this one in particular is called metaphase. And I know you took a test on this recently, but just bear with me for a minute, because I want to give you a real-world example. During this process of the cancer cell dividing, its goal is to make two daughter cells, right? Here you have all the chromosomes lining up at the equator. We have the nuclear envelope has disappeared. We have the centrioles on each end, which is eventually going to split off into two different cells. But before that happens, you have these things coming out of the centrioles that bind to the chromatids, pulls them apart, because we want the same amount of genetic information on each end so that the two daughter cells will be the same. These extensions are proteins. It's a protein polymer called microtubules. Well, we know from natural sources, from bacteria, from certain plants, that there are compounds that are called microtubule inhibitors, or we'll just call it MT. What if we could deliver that